Hello, good afternoon, everyone, or I guess good morning or good evening, depending on where you are in the world. I'm in Boston, so it's good afternoon, a cold good afternoon to me. Um, Hi, Michael, good to see you. Michael is here with me, Michael Goin. He's our principal here at Red Hat and also a vLLM maintainer. If you are new to office hours, welcome. If you've been here for a while, you're very familiar with Michael and myself. We're joined also by Burkhard from IBM Research. He'll be our special guest today. After Michael and I give the community update, Burkhard will go into the vLLM-Triton backend, sharing how do you get state-of-the-art performance on NVIDIA and AMD GPUs with just Triton. We're really excited about that. We also have one more special guest, and Shubhra might miss here. We probably should have added your picture. I can update that later. We also have Shubhra Pandit. Shubhra is in the Red Hat model optimization team, and she'll be sharing some of the new NV FP8, correct, model, Shubhra? Or FP4?
NVF4,
Or exactly models that we just released recently. So she'll share, how do you find those and what's the magic behind those and some of the performance metrics as well. We got decent amount of great actually feedback across social for these releases, so we're happy to share this with you as well. So we'll do that right between Michael and Burkhard's session. So I'll go to the next slide. So we are still expanding on our office hour schedule. So today we'll be talking about vLLM-Triton Backend. In 2 weeks, we don't have a special topic, at least yet. That could change, but we could go back to our original roots where this was a place, and it still is obviously a place for people to ask questions and have a discussion, but we could also, do that on the 26th and just keep it to the vLLM project update and have any questions you guys have. You can totally bring them here. On March 12th, so 2 weeks after that, Michael and I will be in Vienna for the Vienna vLLM meetup, and we're hoping to live stream that. Agenda is still being solidified, but we'll share that with you guys next time. And then on March 26th, AMD will join us to talk about latest trends in AI agent applications. vLLM. It's being recorded. All of the recordings can be found on YouTube. The link is, we have a link right here in the deck, so please check those out. Also, all of the slides are in the YouTube descriptions. And if you can't find anything, you can always find me in the vLLM Slack, and I'll point you in the right direction. So with that, Michael, I'm going to pass it over to you.
Thanks a lot, Sasha. And hey, everyone, good to see you again. Yeah, we have a lot of announcements, new models, blogs, and various things to cover today over the past 2 weeks. Unfortunately, not a vLLM release for you. We're still working on 0.16. We did release a patch release, 0.15.1. So if you're using 0.15, very much recommend taking fixes there. We use semantic versioning, so it's just cherry picks in 0.1 releases. But yeah, let's go ahead and get started. So as Sasha mentioned, we have a lot of vLLM meetups lined up for this first, these next 2 months, I guess. So definitely looking forward to see you there. If you're going to be there, let us know if you're near any of these cities where we currently have ones planned, and let us know if there's specific places you'd like vLLM meetups to be hosted, and we'll try our best to bring them to you. So maybe we should take a step back and make sure you know what vLLM is. So if you're new to the project, it's the open source standard for high throughput, memory efficient serving or inference of large language models. It's the most popular engine for that, and used widely in the open source AI community and also in production by many enterprises, and also as a base for a lot of research in ML systems to fork and build upon and add new methods and optimizations on into vLLM as a demonstration platform. It has over 70,000 GitHub stars, which I think was just over this past week. We reached that milestone. Over 2,000 unique contributors have landed code in vLLM itself, and we have a very large Slack community where you're very much welcome if you want to partake in development or let us know issues or features you need. Those contributors are made from a vast array of different companies. I have over 50 major companies, and a lot of them represented here, although not all of them. And the reason why it's so popular is because, of course, it's open source. It's Apache 2.0. Also, a Python-based library, very easy to install, built on top of PyTorch. So it fits well within that ecosystem. Can load, over 100, if not 200 architectures now, in a very compatible way with the rest of the ecosystem. We work very well with Hugging Face transformers using the transformers backend that's integrated in vLLM as well. So, able to run a large variety of models and architectures, particularly the ones that are launching day by day now. And we'll go over some of the state-of-the-art new open source models out there. But also run those models efficiently on, not just NVIDIA hardware, but AMD hardware, Intel, Google, AWS, IBM, Baidu, the list goes on. And to efficiently run on multiple amounts of those accelerators with different types of parallelism, model, internode and intranode, to scale up your state-of-the-art MOEs to cluster scale inference. And then finally, vLLM isn't just a single project. It's also an ecosystem of projects within the banner, where we have vLLM-Omni now, LLM compressor, guide LLMD, semantic router. Hopefully, you've seen some of those in the community and in other office hours, and highly recommend checking them out if one of the things sound interesting. So now I'm going to cover some updates over the past 2 weeks. We had this nice sort of quick tip where we've been working on context parallelism for a while in vLLM. The sort of decode context parallel has been around for quite a few releases now. But we have been working on pushing performance for it, and also expanding it to not just work for models like DeepSeek or Kimi with MLA attention, but also GQA, or sort of more standard or more common types of attention. This is really useful when we get into more modern models that have a very small amount of KB heads. And when we're parallelizing the model across GPUs, we often want to use tensor parallelism, and we need to split across the KB head dimension. And for a model like Qwen 3, where we only have 4 KB heads, doing tensor parallelism 8, the KB cache 2 times, because we can only we can only divide into 4 times. But if we combine TP8 with DCP2, then we can prevent the duplication, interleaving tokens between devices, and get a lot more throughput at the cost of maybe slightly decreased latency. So if you've ever run into this problem before, where your TP is your tensor parallelism is limited by the model, give DCP a try. Next, a really cool model release from Mistral. They released this Voxtral Mini, which has been an interesting series from Mistral. But most notably, this is their real-time model. And it's one of the first examples in open source of a truly streaming input, speech recognition model. So that's speech to text. And we did a lot of code development with Mistral in vLLM to add real-time streaming input support into vLLM, not just in the front end from the API server level, but also natively in vLLM scheduler. So this was a really important design, consideration and evolution for vLLM to take part in, and we're really thankful for Mistral and Meta and others that took part in the design of that. And actually, building on top of that, just a few days ago, we released a blog co-authored with them on essentially the design of streaming and the real-time API in vLLM. So there's some great sort of insights and diagrams and such, walking through why is real-time an important use case. Hopefully you understand that. But what is this change that we need to consider in vLLM from what was standard in the scheduler before, and now how do we deal with interleaving new input while also producing new output constantly. So if you care about LLM serving systems and hopefully the future of them as they develop, really interesting blog to step through. Next, we mentioned vLLM-Omni before. This has been a rapidly growing project using vLLM for omnimodality, or specifically doing multimodal input and multimodal output. And it's had its first stable release with 0.14. And this has also coincided with the paper release on arXiv, covering the project and architecture and justification for it. So highly recommend checking it out on arXiv, and also trying out and downloading the release yourself, and trying some of the new models and APIs that have been added, and hopefully contribute to some issues. Yeah, so love to see the progress there. Next, we saw some nice developments from ML Commons and the MLPerf inference round, which is finishing up here in a week or so. And we should see those results, I think, in hopefully sometime in March. And we're really happy to see that there's a new multimodal, a vision language model benchmark finally added to the inference using Qwen3VL and Shopify data. And I recommend reading the blog. It's a pretty interesting, thankfully, like, transparent case of, a real use case that Shopify has for vision language models at scale. And really cool that they could, share their use case, share a data set nonetheless, and publish this as an open source benchmark. And a lot of us on the vLLM team have helped sort of guide, like, what is the right model and reference implementation and benchmark to set up here for vision language models. And as you can see, vLLM is the reference implementation. So we're really happy to see that, and yeah, really excited to see the submissions and how much performance people can push vLLM on the latest hardware of the day. Next, we have a blog in collaboration with NVIDIA, where we covered some of the performance optimizations we've done on NVIDIA Blackwell B200 and B300 GPUs for GPT-OSS. There's a lot to cover there. New attention kernels, new MOE kernels, a lot of kernel fusions, development and async scheduling, and even streaming token output optimizations on the API server. Yeah, all of which is dove into pretty deep detail on the blog itself. So recommend to read as well. And on this graph here on the right in Inference Max, we were able to improve the Pareto frontier of performance, both in terms of token throughput per GPU and also interactivity, or latency for each user across the board. And we have a lot more planned. But great to see this development over just a month or so of optimizing on this benchmark. Next, we had a pretty big blog from NVIDIA and Meta pushing DeepSeek R1 wide expert parallelism sort of wide EP and disag PD deployments with DeepSeek R1 on GB200. And another great example of a deep dive into what sort of kernel optimizations and system optimizations had to be made in vLLM to support this new, faster platform. And then also, of course, great performance insights into the benefit of moving from H200 to GB200, not just in terms of the GPUs themselves, but also the interconnects between them that allow for much higher bandwidth now with NVLink across nodes of GPUs, or in sort of this NVL72 domain rather than just NVL8 with H200. So yeah, again, if you're interested in DeepSeek level deployments, and particularly the latest generation of Grace Blackwell, highly recommend this deep dive into the value of those platforms and the work we've already worked on and are working towards on top of this, optimizing for this new generation of hardware. Next, I'm going to get into quite a barrage of interesting open source model releases. We've had quite a few, state of the art and also, just very powerful models for their size and class and speed. First one up is a model from StepFun, Step 3.5 Flash, which is kind of small, at least in terms of the recent large-scale MOEs. It's only 196 billion parameters. But it has a very, very sort of sparse activation, only 11 billion parameters activated per token. And so, and of course, like really good agentic evals and training was done for it. So, sort of a very efficient model for, the scale that it's at, and sort of this intelligence density graph, I think covers this pretty well with some contemporary models and models like Claude or Gemini. Next, a really, really small model from the ZAI team, GLM OCR. I think this is, 0.9 billion parameters, and a very, very impressive model for vision language modeling, particularly focused on OCR, optical character recognition. So turning PDFs into structured text, hopefully. And you can see it has some amazing looking benchmarks against Gemini 3 Pro and GPT 5.2, which are certainly not 1 billion parameter models. Really impressive work. And I think this has been like the top trending model on Hugging Face actually for the past couple of days, with a couple 100,000 downloads over the past month. So, and a lot of that done on vLLM. So really happy to see, performant vLLMs growing on vLLM. Next, we have an update from the Qwen team, Qwen 3 Coder Next. You've probably seen Qwen 3 Next before. This is their, coding version of that. Also a very, very capable, coding or agentic focused MOE. Only 80 billion parameters with 3 billion active params. So, and of course, this next architecture having a very fast form of linear attention with gated, with GDN, gated delta networks. Used for attention rather than standard self-attention. So, very fast at long context, small KB cache, all those great things, and really fast on local hardware and also, hosted on data center hardware. So, really impressive release, and very much looking forward to the next models from the Qwen team, hopefully coming soon. And most recently, we had GLM-5, a new, state-of-the-art model released by the ZAI team. You see here they compare with GLM 4.7, which I think was only like a month or month and a half ago. And this is a new state-of-the-art model competing with the likes of DeepSeek and Kimi K2 2.5. And the key thing here is that it's actually the first model other than DeepSeek to adopt the DeepSeek sparse attention, or rather kind of sparse MLA. So it uses this with also support for MTP, for speculative decoding, built into the model, and seemingly very capable long context and agentic tool calling, coding support. As you can see here from some of the graphs, going up against the likes of Claude Opus, Gemini 3 Pro, and GPT. So really glad this release went over well. I think yesterday. So really great to see new models, and love the progress here. Now I'll hand it off to Shubhra to cover this research and recent blog.
Yeah, thank you, Michael. Hi, everyone. My name is Shubhra Pandit, and I'm from the ML research team at Red Hat, working on model optimization. I'll briefly walk through our latest NVFP4 model release and what that means for large-scale deployment. So while NVFP4 support isn't new, in vLLM, we've produced and released a broad set of NVFP4 models, ranging from smaller models up to large, dense and NVMe architectures. At a high level, with NVFP4, we're compressing both weights and activations, input activations down to 4-bit floating point. Now, this significantly reduces model footprint on the order of roughly 3 times smaller than BF16 and up to 1.8 times smaller than FP8. So this reduction matters because, as we know, for large model inference, model memory often becomes the limiting factor. So when weights and activations take up less space, you effectively free up GPU memory headroom, and that directly translates into higher batch sizes, better concurrency, and overall more efficient deployment. And for larger models, especially 70 billion and above, this reduction materially changes what's practical to deploy while still preserving model behavior. So one of the reasons why NVFP4 works really well is because of a hierarchical scaling strategy. So instead of a single, 4-bit compression regime, we have smaller groups of roughly 16 values per block, and each of these blocks has its own FP8 scale, and then the entire tensor additionally has another high precision scale. So the combination of these two scales preserves the dynamic range that would otherwise be lost at such low precision. And because the block size is so small, just 16 values, NVFP4 can adapt to any localized variations in tensor distribution, which also helps maintain stability, when the values are more heterogeneous. Now, on the accuracy side, the main takeaway that we saw is that recovery improves with scale. And we evaluated these models across various benchmarks like OpenLLM, HumanEval, some reasoning benchmarks as well, and coding with HumanEval. And the pattern that we saw was pretty consistent throughout the models. So the large, dense, and MOE models, 70 billion and above, these typically recovered around 98 to 99% of the PF16 baseline accuracy. The mid-sized models were close behind, while the smaller models, they showed a bit more variability, which is fairly common to see with these ultra low precision settings. But the overall trend, again, was pretty clear. As the model size increased, the quantization became more stable. So another encouraging thing here was that the large models, they generally required very minimal tuning. In most cases, standard NVFP4 recipes were sufficient, and this helps, especially with the large models where manual tuning would really take a lot of iterations and experimentation to get a good model. So with large models, we didn't really have to do that. Beyond the accuracy trends, we also applied this NVFP4 quantization to a broad range of architectures and sizes, covering models from 8 billion up to like 400 billion param range, and different families from Llama, Qwen, Mistral. And so it kind of spans the entire range of models. And now all of these models, they are available in our Hugging Face NVFP4 collection. It's linked here in the slide, and they are deployable in vLLM. So the most benefit that you'll see is on the Blackwell GPUs. Let me see. Yes, MXFP4 was also looked at more so by another team. I think they found that bigger group sizes worked better with that. So I think what we focused was more on NVFP4 because we had support for that on the V200 systems, and we were kind of focusing on that. So this, I hesitate to say that all of these settings broadly applied to MXFP4 because there were some differences there that we're seeing. But I can definitely dig that up and share that across as well. So all these models are available in our Hugging Face model collection. Go and take a look at that, explore these, and they have detailed model evaluations in the model cards as well. And yeah, the best performance gains that you'd see with these models are on the Blackwell GPUs. And there's a blog as well that dives more into the benchmarks and per task results if you'd like to take a deeper dive into that. So that's all I had from the NVFP4 model release standpoint. Please feel free to drop more questions in the chat, and I'll try to address them. With that, I'll hand it over to Sasha for the next section.
Thanks a lot, Shubhra. I will actually hand it to Burkhard for the guest topic. So thanks a lot for sharing. Burkhard?
Yeah, thanks, Michael and Sasha and Shubhra. Yeah, also good morning, good afternoon, or good evening from my side. I'm in Zurich, Switzerland, so for me it's nighttime, but I'm very happy to be here in the first time for this vLLM office hour and very excited to talk about the Triton backend we contributed over the course of last year to vLLM. And for this, I plan for the next roughly 25 minutes to cover first the basics. So why does Triton actually help vLLM? Then what is this attention backend in vLLM? And who uses it. And then we slowly get more technical and talk about how to implement a high-performance page attention kernel in Triton, the tricks we use, and even covering system-level things like launch grid and CUDA graphs. In the end, I show some benchmarks, and we can maybe also discuss Helium. And yeah, then let's see. So cover the basics first. I assume everybody heard about Triton. If not, in one sentence, Triton is a domain-specific language where you can write a kernel like matrix multiplication or attention in Python, and then this Python code gets compiled to different GPUs. And how does it help vLLM? Well, as presented by Michael before, vLLM aims to have the best possible performance on any platform with any model and any parallelization and so on. So you know the marketing quote. And that means we also need the best possible kernels on each GPU platform. And to do this, we have usually two ways. One is to write tons of custom kernels, so like 100 different kernels for 100 different models on Blackwell, 100 different kernels for 100 different models on Hopper, and 100 different kernels for AMD and so on. Or we try to write few kernels that are performance portable. And performance portable means in this field that these kernels adapt automatically to different hardware and then have the ability to operate best automatically on different hardware. And that's where Triton comes in. So in a nutshell, Triton's programming model, which is around tiles and right abstraction level, helps us to allow us to either express really complicated kernel optimization still, so it's not too high level to not be able to express low level optimizations, but it's not too low level to not do this in hardware agnostic way. So it somehow sits nicely in between. We can optimize it, but we can stay flexible for different hardware. Why is that so? So on the right-hand side here, I showed you, I put one line of Triton where we define a 2D block that then can be used for a matrix multiplication, for example. In Triton, you use these ranges to do so, but that's it. So that's if you as a programmer. The compiler then decides, okay, to break down these two-dimensional block into two bigger blocks here on the hypothetical GPU 1, or to break it down into another 4 blocks that are much wider but thinner on the other dimension for GPU 2, because that's more optimal for this platform. And that's done by the compiler automatically, either the compiler or together with the autotuner of Triton. So because then actually Triton runs different experiments to try out what block size is best for different GPUs. And that helps a lot with this performance portability as well. So that was Triton in vLLM, and there are actually a lot of Triton kernels in the meantime in vLLM. So now we go more in the direction of the attention backend, and actually the attention backend is not a big thing. It's about attention, like attention is all you need. So vLLM decided roughly a year ago to wrap the attention-related code in a specific abstraction or API called attention backends to separate it from the more simpler linear layers or layer norm, because there are many attention backends, and that way the architecture gets easier, and layer norms usually are not so complex and not different libraries for them. So there are multiple attention backends in vLLM. So for example, flash attention or flash infer for CUDA-based platforms, and there is a ROCm attention backend as well that uses ATA kernels. Then there are different attention backends for MLA attention or so, and there's a Triton attention backend that is written only in Triton. And why did we start this project roughly a year ago? So why yet another attention backend? Well, one of that thing I covered before, it's about performance portability. We try to make our platform also for our customers as performance portable as possible for any number of GPUs, not only the latest and greatest from some vendors. So, and the Triton attention backend runs the same source code without any adaptations needed by the user, runs on NVIDIA, AMD, and Intel GPUs. It is also native in vLLM, so it's not an external dependency. And yeah, it's in the meantime more or less owned by the community, so to speak. We at IBM Research started it together with Red Hat, but then in the meantime, we have many contributions from the community. Yeah, so thanks to you, you're here. And that's also how the Triton attention is used, I guess, for a large number of cases. It is the default on AMD GPUs and then used in specific scenarios, like, for example, if you have float 32 on Intel GPUs, or if you have models like the step fun model earlier presented by Michael that uses a special feature called square root alibi square root, sorry, or the GPT OSS model, if it's used on non-Hopper or Blackwell GPUs, so like A100 or L40s or AMD, then we need the sync tokens, and that's supported by the Triton Attention backend as well, in contrast to other backends, and so on. One nice thing about the Triton backend is it is some kind of fallback. So even then you cannot install Flash Info, or the installation fails, or vLLM fails to import it, it can fall back to Triton Attention backend because there is no external dependency. It just depends on PyTorch, like vLLM itself, and it is always available. So, and also it supports in the meantime features like batch invariants and so on. So after covering this baseline, we now get a little bit more technical, and I would like to discuss a little bit how to write a high-performance kernel for page attention in Triton. And when we started this project, a little bit more than a year ago, we actually didn't start to write it end-to-end in vLLM. We first decided to write a small kernel and then make sure the API of the kernel is compatible to what vLLM needs at that time, but then use micro benchmarks to test it extensively. So to test a wide range of scenarios, pre-fill heavy batches, decode heavy batches, mixed batches, large batch sizes, and so on. And for us, it was really important to use these micro benchmarks because they helped us to look into these details a lot. And I brought you here an example on the right-hand side, and I think I cannot mark on this slide. But if you see here, we have now flash attention and 3 different versions of our kernel in these plots. And this plot is on the x-axis is the number of tokens, so batch size times tokens in the batch. And on the y-axis is the latency. And then we have different subplots that say, okay, if it's a prefill only batch, a mixed batch, or a decode batch, and you see, depending on the scenario, all different versions work differently. For example, the blue one, which is highly parallelized, I come to that later, is the best for larger, long and small batch size and long context, or larger batch size of small batch size long context for decode, but actually performs poor in other scenarios, versus the purple version here performs good for small decodes and prefills. And to have these detailed insight with micro benchmarks helps us to define the right heuristics to use that end-to-end in vLLM. Of course, end-to-end, I don't say we only should do micro benchmarks, because end-to-end benchmarks are really important, because that's what the user cares in the end. And also, you can have the best possible kernel. If the kernel doesn't fit the system where the kernel is used, then you also don't get far. So you need to make sure that it fits in the framework and that the end-to-end results are what you expect. But sometimes end-to-end results are also misleading. So they cover specific latencies of the kernel because there are other bottlenecks or so. So it's good to have always both views, micro benchmarks and end-to-end. Then for page attention specifically, I listed 3 optimizations here, and I will cover all of them in detail in the following slides, just to list them here in the first hand. We need to optimize the tile sizes for TL dot operation. Then we needed to think about how to increase the cache reuse, especially for group query attention models. And as you already see in this micro benchmark here, carefully think about the trade-off between parallel versions, so like the blue and the purple version, which uses different kind of parallelizations. Besides that, I mentioned already autotuning before, and of course we use autotuning in Triton a lot, but not in production end-to-end, because autotuning in Triton, is rarely done ahead of time, so it's done a little bit unfortunate if you want to deploy it one-to-one live. So what we do is we do autotuning in our micro benchmarks or test scenarios end-to-end, and then look at the decisions of the autotuner. So what did the autotuner pick as best possible configuration? In which scenario? We analyzed that and trained decision trees on it, or that maybe sounds more complicated than it is, because right now we settled on if-else decision trees. to say, okay, for prefill heavy, for decode heavy, for AMD GPUs, for NVIDIA GPUs, so that are roughly the cases, we pick different configurations and therefore adjust the Triton kernel automatically for different situations. But yeah, that's based on auto-tuning, and that helps a lot in getting high performance Triton kernels. One technical footnote here is we need to make a trade-off as well, because these cases we selected and heuristics we selected for configuration selection don't go to 100% possible performance. It maybe go to 95% of the performance, but usually that is good enough for all use cases, and it ensures that VLM has a small startup time and doesn't start up for hours, but still deliver 95 to 97% of the performance. So, as promised, I will go into more details about the optimizations mentioned here in the middle, but we also wrote a paper with even more details about this, the anatomy of a Triton attention kernel, and posted on arXiv. So if you're interested in learn even more details, check it out there. So just before we go into details, for those of you who don't write page attention kernels daily, quickly what these do. So attention itself is a performance critical kernel of LLM, so where the LLM learns to understand which words belong to which words and so on. And page version means VLM tries to do it in a memory efficient way. And in this page attention, what we need to do is that we have a batch with multiple queries in it. And for each query in this batch, we need to process each token of this batch. And that's depicted here on the right-hand side in this figure, where the query tokens are on the x-axis, down in the bottom, and then we need to process all these tokens actually from each query. And then on the y-axis, depicted on the figure, is the next level of work we need to do is for each query head, we need to process each token. And then, of course, you need to go through the context in the KV cache, which is paged. And yeah, that nested four-level for loop, actually, once you set this up, then you arrive at the attention computation and do the multiplications. This figure is a little bit simplified, so it does not show masks and sliding window and so on, but it shows how to think about, okay, if you have this multi-dimensional problem, how the kernel picks its workload and goes through each axis and solves it. I cannot go into full detail here in the interest of time, but a colleague of ours, Tom Parnell, wrote a blog post about how this runs on the PyTorch blog, so if you want to know all the details, check this out. Or the paper I mentioned before. So now promised, we getting more technical. What are some of the tricks we apply to get the best performance out of it? Well, one of the things is we need to get enough parallelization in the matrix multiplication itself, because that's critical. And the matrix multiplication is done with Triton with the operation TL ... And this is very well optimized by Triton, but in order that it is good optimized, we need to give it a lot of data. So if we give it only a vector size of 2 and 2, then there is not much this operation can optimize. So we need to increase the data we feed to this on the tile sizes we feed to this operation. So this matrix multiplication has two sides. On the K side, so from the KV cache, we actually limited by the page size. So we try to optimize on the Q size a little bit more, and Q, the query, we can process multiple query heads at once. And here for group query attention, it's obvious that we should optimize the cache reuse and fetch all the query heads that belong to one KV head at once. And then that was not enough parallelization, so then we decided to add multiple query tokens as well as one work package. And this one work package is here depicted on the right-hand side in this three-dimensional Q block, because of course we fetch a complete head dimension. And then we launch multiple kernel instances. So that is here depicted by this launch grid with the batch size and the number of KV heads as 2 dimensions of the launch grid. And then we launch as many instances of the kernel at once to get this work covered. Of course, we needed to combine this with auto-tuning. And for example, for Llama 3 with 32 query heads and 8 KV heads means we can reuse always 4 query heads, 1 KV head. For H100, the block size of M in 1 dimension is 4. And then it turned out we need to fill even more query tokens to utilize a TL ... In this case, it was 4. For MI300, they have a different memory architecture. So there we can even go in the other dimension to 64, and we can process 16 tokens at once in 16 query tokens at once. And this you can also find in the code. So that was one optimization to really utilize the matrix multiplications well. But then if you notice, okay, processing multiple query tokens at once doesn't work for decode, because there we have only one query token at once. So here we need another way of parallelization, and that was especially done by my colleague Jan van Lunteren here also in Zurich, and where we said, okay, in the earlier versions, if I go 2 slides back, here you see, okay, we have a 2-dimensional launch grid, but the 3rd dimension we process within one kernel instance. So we launched a kernel to process the 2nd query token here, and the 4th KV head with a 4 to 8 query head, but then through the KV cache we went sequentially. And the parallel tile softmax changes that, so then we even split up this 3rd dimension, so that's why it's called 3D kernel. However, that requires that we then reduce the results later, so we have only partial results in each kernel instance, so we need to store them back in the GPU memory and then launch a 2nd kernel to compute the actual results. So this could be done with a global barrier, but Triton doesn't have a global barrier, so that's why we needed 2 kernels. And this, of course, creates another trade-off between, okay, when is it worth to launch 2 kernels to do this versus not? And of course, okay, for longer decodes, it's worth, for others not. So, and we try to find a good heuristics for that. But also at this point, we noticed that maybe CUDA graphs can help. So, because one way to reduce the launch overhead of 2 Triton kernels is to have to record them as CUDA graphs. So we looked into how vLLM is using CUDA graphs at that time. I cannot go into full details here in the interest of time, but just briefly. So if a CUDA graph records the kernel launches on the GPU and then stores, I wouldn't call it mega kernel, but like a big blob binary in the GPU memory to replay these kernel launches. And that's very good for inference, because in inference, we rarely change the model architecture from one pass to the other. So there we can record one inference run and execute it. However, that doesn't count for attention layer. Especially all the optimizations I already showed you shows you that, okay, depending on the batch size, decode, prefill or decode, we use different kernels. So there, vLLM had in the beginning only piecewise CUDA graphs. So meaning only the linear layers were in CUDA graphs, but attention was then run eager without CUDA graphs. But throughout 2025, vLLM decided to also enable full CUDA graphs for the complete model in different scenarios, and if the backend supports it. And of course, there's another trade-off, because CUDA graphs recording fractures the GPU memory and uses up GPU memory. So yeah, there's another trade-off, and somehow vLLM decided on a magic number of 56 CUDA graphs that they record for different batch sizes and so on. Yeah, one thing to know about CUDA graphs is if you record this kernel, then it gets frozen. So the arguments you pass to this kernel, including the pointers in theory, are frozen, and you cannot change this anymore. You just replay the exact kernel again. So you need to change the content of the pointers. And also this includes the launch grid. So the 2D and 3D launch grid I showed you earlier is also frozen. And yeah, all of these trade-offs are very well documented in vLLM. Of course, it's maybe a little bit boring to point to the documentation in office hour, but I think vLLM actually has a very good documentation from the open source projects I worked previously. So it's, I guess, also fair to point this out. To continue with the page attention and to get one level deeper into the system, to understand this trade-off a little bit better, you need also to understand how GPUs schedule these different launch kernels, because if you launch 100 kernels in parallel, as 100 instances of the same kernel in parallel, they cannot be executed in parallel. So they can only be executed as many cores, or NVIDIA term would be streaming multiprocessors the GPU has. And then these cores are fully utilized, and then one after each other, one round after other, trying to process threads that were launched. To explain this, I have used now SM, so streaming multiprocessors, which is an NVIDIA term, and also I use an NVIDIA figure here on the right-hand side. And if we imagine that a GPU has 8 SMs, so there's a typo on the slides. I will fix it later. So if this GPU has 8 cores and we launch 12 threads, then what happens is that the first wave, so the first round of threads is executed in parallel. And then we need a second round of execution, what is called in NVIDIA terms wave, to execute the remaining 4 threads. And as you can see, this waves here, I marked this already in red, 4 SMs that don't do anything at that time because they cannot be shared to other programs and so on. There's a footnote to that. Modern GPUs like Hopper and especially Blackwell changes this a little bit, but yeah, in principle that holds. So if we record this launch of 12 kernels, 12 threads now as a CUDA graph, we always replay the same 12 threads. Meaning if we have, and if these 12 threads, for example, process 12 tokens, but now in the next round we have only 4 tokens, we still execute the kernels as if there would be 12 tokens. So, and we waste even more compute resources as depicted here in the orange part. Of course, the second wave can exit early, but still we lose some latency. Of course, that does not always matter. And I mentioned before that we don't record one CUDA graph, so this is for the complete model, but actually for each batch size of power of 2, vLLM records multiple CUDA graphs for long and short prefills and so on, and only decodes and so on. And so that is not as critical as it may sound, but it's some careful trade-off you need to think through if you design a complex kernel like page attention. And how did we solve this? Well, the obvious solution is to make the launch bit not flexible, so that we not launch like, I don't know, 50 instances in one inference, one forward path, and then the next forward path launch 100 instances or 80 or so, but that we always launch exactly the number of instances that are cores available, so that we fully utilize the GPU and not produce any tail waves. And that changes the program model a little bit. In theory, it's simple because it just adds another loop around this kernel. So instead of launching multiple kernel instances, as in the figures above, we launch now as many instances as we have cores on the GPU, and then each kernel instance itself figures out how many tokens there are to process in this round. So that means the CUDA graph stays the same, the kernel stays the same, the launch bit stays the same, and each kernel is a little bit smarter, a little bit more complex in figuring out what needs to be done. And yeah, one detail here is, of course, the arguments to the kernel are frozen, so we cannot pass the information how many tokens this instance need to process as scalar. You need to pass it as a pointer to a memory location that you can update with the metadata. And yeah, then you have a persistent kernel that utilizes the GPU in the best way with CUDA graphs. So if you execute in eager mode, you don't need it. So yeah, that was more or less what I wanted to cover technically. Now, of course, I want also to share some benchmarks from the time when we worked on it in August and September last year, and also presented this at PyTorch conference. Here you see the same end-to-end experiment with Llama 3 8 billion with batch size of 1, so really to see the latency and input length of 500, and then decode length as depicted on the x-axis. You see left-hand the H100 and right-hand MI300. You see on the left-hand side, Flash Attention version 3 as baseline, as a state-of-the-art kernel on Hopper. And then you see 4 Triton versions that more or less represent our learning curve. So in the beginning when we started this project 1 year ago, this purple baseline here, we were roughly 6 times slower than CUDA, the CUDA kernel. But over the course of our learning and experiments that I presented to you earlier, we actually managed to match on Hopper the performance of Flash Attention 3, actually a little bit, 0.7% faster on this benchmark for very long decode requests. And on the MI300, there is no comparable, or at least was not a comparable kernel. So, but also there we improved roughly 6 times over 6 months. And yeah, what I want to point out here is that it is the same kernel running on both GPUs. So we don't And that is in contrast to Flash-Attention 3, right? Because our Triton kernel at that time was roughly 800 lines of code. And the Flash-Attention 3 kernel uses 70,000 lines of code to execute the same performance on Hopper, which is wrapped in roughly 500 different kernel versions, right? So that's the opposite of performance portability. And yeah, I also talked about micro benchmarks before a lot. So just briefly show you here some micro benchmarks. And yeah, left, you see again H100, right, you see MI300. And on the top and bottom row, you see the same data, but sorted differently in subplots, right? So on the top row, we had the batch size and the x-axis, and then the subplots are different sequence lengths, as a maximum sequence lengths in the batch, versus on the bottom row, we have the same data, but we sorted the data if it's a prefill or a decode case. And yeah, as you see, the results present itself very differently, depending on which angel you look at. And that, as discussed earlier, that helps us a lot to understand, okay, in which scenario, which kernel is better, and actually, did we improve our kernel in this round? Yeah, maybe briefly, maybe you heard about, if you are into this topic, then you heard about Helion. So Helion is a new domain-specific language released from the PyTorch team. And you can think of it like tile PyTorch or higher level Triton. So it sits a little bit between, and it aims to have even more performance portability. So we, of course, were curious in how to work with it, and we wrote the same kernel I just presented to you, or a little bit simpler version of this kernel in Helion, and achieved pretty good results with it, and also published a blog post at the PyTorch blog about it. The code for it, actually, you can check out in the vLLM repository. It's a draft PR. Yeah, so that's maybe some way how to develop this further, but it's very early, of course, but it's very cool to work with. So I recommend this blog. And yeah, I guess I hope I could plant some excitement about performance portability and the vLLM-triton-backend. I hope I covered some interesting details, and now I guess it's time to open up for questions.
Awesome. Thanks a lot, Burkhard. That was a really great deep dive and a holistic overview of the progression that you've made over the months and years, I guess, at this point. There's an interesting question in the comment. Have you had a chance to gather any new data on how Flash-Attention 4 stacks up against the latest Triton?
No, not yet. Also, we know that, for example, on Blackwell, Triton has still some performance. That needs to improve the performance on Blackwell still, so we didn't really do experiment there yet.
Yeah, I agree with that. Even within Triton itself, they've sort of moved on to this like gluon middleware, lower, still using a lot of Triton, but not using the front end for Blackwell.
Yeah, that's an interesting, interesting question and point in this time in the community, right? Because we have these two movements with gluon to go lower level and more hardware specific, and Helion to go higher level and more performance portable. So I guess we can accept bets in what will turn out to be the superior approach in the long run.
Yeah, I'm definitely interested in Helion a lot. Maybe for attention, I'm a little, a little more cautious about it. But it's certainly,
Also in the beginning, I had, in this blog post, I guess I reached 90% of performance in Hopper. But in the meantime, I played with it a little bit more, and because now I found an optimization Helion, and that maybe can improve the Helion compiler, where we have, because in Triton we always need to decide use this 2D kernel or 3D kernel, right? These two optimizations I presented before, and there are scenarios where none of that is optimal. But with Helion, we can have an approach where we have something, a mix of it actually, so a 2.5 dimensional kernel. And because the compiler can compile this, and this actually outperforms Triton on our Triton kernel on Hopper for long prefills, for example. So I guess a lot of experiments still to be made. And
development, because it is sort of a new level to invest in.
Yes.
There's another question, like, what's the adoption of Triton like? Are developers moving to Triton from CUDA? I mean, I can speak for myself. I definitely, both myself as a kernel writer and also as seeing the community. There's been a lot of people writing Triton, and I think it's also like a much easier starting point for people than writing CUDA. It's also much faster, right, to iterate in. You're staying in PyTorch. You're staying in Python cleanly and quickly with PyTorch, and then now with like Torch compile, using Triton as the inductor backend for code generation, it's like, I think it's pretty clearly like a very, very strong language and library and runtime for generating kernels. I think there's obviously the question that like, is it good enough for like matrix multiplication as hardware becomes more and more harder to write matrix multiplications for, or complex operations like attention? Sorry, is there an issue with my mic?
Yeah, you sound a little bit robotic. I think I got what you were saying though, but it was definitely an issue.
Yeah, maybe Burkhard.
Okay.
Yeah, you're back. You're back.
Yeah, I guess there's no general answer to this first question. And what I like especially also about Triton is it stays in Python. It is vendor agnostic, right? We covered that, but also you can simulate your kernels, right? So if you are unsure if you need to debug and you have no idea what's going wrong, then you can simulate the Triton kernel, executing it in NumPy. And that at least then you can verify that your kernel logic is sound, which I think is a cool feature also. Yeah, maybe going to the next question here. Yeah, between Cutlass and Triton, I guess Cutlass is also a library of kernels. So I guess that depends on the use case, right? Depending on which GPU platform you want to use, obviously. And yeah, if you are experienced in Triton and writing a high-performance Triton kernel, or you prefer C-like languages like Cutlass. I actually never use Cutlass myself, or actually only a little bit, I have to admit.
Yeah, I can definitely say Cutlass is a lot harder and overall like less flexible. Like basically I wouldn't consider Cutlass at all if you're not writing like a gem, or like a matrix multiplication essentially. Like if you're doing element-wise or quantization or like memory-bound operations, it's kind of not that useful. Also has some like low latency sort of issues. We use Cutlass a lot. I think that's part of the reason why we're a little bit more excited for like QtDSL and the Pythonic Cutlass that it's been developing there. But again, it's very specific to NVIDIA GPUs and isn't going to work on any other hardware. And is usually, certainly true for Cutlass. I think also true for QtDSL. You're writing it for a very specific architecture of NVIDIA GPU. So you need to write different kernels for different GPU architectures.
And especially also for specific scenarios, right? So the lower you get in your language, you also need to optimize for symmetry of a matrix, right? And if you then use tensor parallel and your symmetries of your matrices of your model is suddenly different because it's sharded across GPUs, then the same kernel has actually poor performance. Versus Triton and Helium can adjust better depending on the scenario.
Yeah.
And yeah, going back to the comments here. So yeah, Helium is you feel I'm very excited about Helium, but I guess it's still a little bit early. So for production use case, I don't know yet. But also vLLM is adapting Helium, and we have already some early infrastructure to incorporate Helium into vLLM in the past weeks. So that's also very exciting. Then I guess from Ryan here, a very important question. And if a newcomer should use CUDA or needs knowledge of CUDA or should directly move to Triton, I actually would recommend start with Triton or PyTorch, because in CUDA, you need to know a lot of details of pointers and of the semantics of this language. And in Triton, this is covered away. So you still need to understand what an SM in the GPU is and what these threads are to some extent. but only a little bit. So you need to understand, you need to write a parallel kernel, and Triton has a single program, multiple data programming model. So that you need to understand. But that's it, actually. You don't need to understand all the low-level details of the grid in the first place if you start with it versus CUDA. So that's why I would say, yeah, that Triton is the easier way to start versus CUDA. But
yeah, I would also 100% agree. Although I would like I would specifically advocate for writing in like a higher level language, something where you're working on tensors, and like something like Triton I think is perfect. But then also like profile and use like Nsight systems and like look at the the PTX, which is like effectively the assembly that we can read that goes to NVIDIA GPUs. And because you can go very deep in Triton nowadays in terms of the specificity you can get with operations and such, as Burkhard has demonstrated. But yeah, it's kind of a similar thing where you want to understand what it's compiling down to and how it's using the hardware, and if there's like clearly like buffer, like inefficient operations happening, and frankly I think kind of understanding from the higher level operation tensor compiler level all the way down to what's actually gets emitted, this is a good way for sort of maybe like speed running, understanding the hardware in like more useful ways, versus getting stuck in like C++, CUDA semantic things.
Yeah, I agree. I think also if you want to get started in this field, in this topic, do the tutorials of Triton, maybe a matrix multiplication, but then add a twist to it, like do the tiling different or do some scalar operation within the matrix multiplication. Doesn't really need to make sense, just that you get your hands dirty, and then use the tools Michael mentioned, right? Like NVSys or NVCompute to see, okay, what does it compile to assembly? How is the hardware utilized by each instruction so that you understand the complete flow? And yeah, then I guess you have pretty much a pretty good feeling what this thing is doing.
Yeah. Well, certainly great discussion. We're solidly over time, so thanks a lot, everyone, for sticking around. Very much to Burkhard for presenting and giving a great overview. Thanks, Shubha, for presenting as well, and good to see Sasha. So yeah, thanks everyone. Hope you had a good past 2 weeks. Hope you have a good next 2 weeks. We'll see you then, and yeah, thanks for being a part of the community.
Thanks for the discussion.